Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Farisha Nabila binti Mazalan, and I will present about the project title Turbine Propeller. For the introduction, what is additive manufacturing? Additive manufacturing is defined as the flow processes of producing part through the deposition of material layer by layer. The versatility in AM's product design helps it to penetrate into so many areas in the automotive, aerospace, and medical sectors. AM may be also represented as a method of combining materials by the process of either binding, fusion or solidification of materials such as powder and liquid resin. Then, it will go through the process of creating part of a layer using 3D CAD modeling. There are a range of widely used forms of binder jetting, material extrusion, material jetting, powder bed fusion, sheet lamination, VAT photopolymerization, and guided energy deposition in AM. Directed energy deposition. From the figure shows the DED as a group of AM processes that simultaneously add material alongside the heat input. A laser, electron beam, or plasma arc may also be the heat input, and the metal powder or wire are the material feedstock. Next, powder DED machines also have inert gas blown from nozzles along with the powder, thus covering the melted area, reducing the oxidation rate. However, the powder DED system can eject metal powders using single or multiple nozzles. The use of several nozzles make it possible to combine various materials in order to get functionally graded materials, FGM. And it is also possible to easily combine DED processes with traditional subtractive processing for finishing machining. DED processes multi-axis deposition capability enables complex geometry components to be produced without supporting structure, such as thin wall structure, refurbishment, and international future components for aerospace component. Next is topology optimization. Optimization of topology is a technique that optimizes the material layout within a design space with the primary objective of optimizing device efficiency. In the manufacture of aviation components, it is a necessity to reduce the mass of single appliance in order to increase performance because design, transport, and assembly problems are troublesome for larger models. The mass of the turbine propeller that is part of the aircraft is included. Minor improvements in blade shape may then occur as new airfoils, tip designs, and structural materials are introduced by manufacturers. A conflict is also evident between improved aerodynamic efficiency in slender aerofoils and thicker aerofoil structural performance. Since the material used to produce this component is made of titanium aluminum alloy and nickel alloy material, the DED method is the most appropriate technique for producing the propeller of the turbine. The objective of this project is to extensively research about additive manufacturing in turbine propeller production. Next, to compare manufacturing technique with additive manufacturing for turbine propeller. And for the last one is to minimize the mass of turbine propeller by using the CATIA software.
Assalamualaikum and good morning. My name is Muhammad Shairan Bihalimi. I will explain about the teacher review. In the teacher review, I will talk about additive manufacturing, what is propeller, and what is additive manufacturing process that used to making the turbine propeller. First, additive manufacturing. Additive manufacturing gives a fitting definition for the technology used to create 3D item by applying contact layer upon layer, whether it is plastic, concrete, and metal. Additive manufacturing is also a manufacturing process that strives to further complicated 3D dimensional structure by successfully applying them. New 3D printing such as sterile lithography (SLA), fused deposition modeling (FDM), selective laser sintering (SLS), selective laser melting (SLM), 3D inkjet printer, binder jetting, and lastly is laminated object manufacturing. What is turbine propeller? The propeller turbine is a turbine for internal flow reaction similar to one of the combustion blade. It is turbine that are common and operate well at a higher flow rate. The volume is a propeller and is equivalent to that with a ship and submarine pizza across the sea. By helical motion, a propeller transforms the energy supply and drives with the power source with proper physical forward and field medium. Propeller also used in aviation from the moment of traveling. The solid panel blade wooden propeller was the first innovation in aviation. additive manufacturing method that use in making propeller. First is laser metal deposition (LMD). This technology allows the development of complicated design components without internal equipment at one technical level. The substance reconstruction developed by LMD approach is certainly different from such obtained by conventional thermomechanical processing technique due to the continuous thermal cycle of material microvolume. Second is direct energy deposition (DED). DED applies an energy source that concentrates directly on one small substrate area while simultaneously melting a substrate feedback. Material used for turbine propeller. First is the previous one is nickel alloy. Super-alloy nickel is as found the resistant to oxidation when subjected to the operating temperature of the motor, including temperature in the inlet of turbine greater than approximately 2200 Fahrenheit. And the latest one is the titanium aluminide alloy. Titanium aluminide has a particular weight of about half that of nickel alloy and is adequate to provide a special force in the region of odd temperature. The technology of laser powder bed fusion provided the titanium aluminide alloy with complex geometry precision for laser analysis. One of our analysis used in this project is FAE analysis. Finite element analysis is the separation of units of mathematical procedure called the finite element or FEM process of a physical phenomena. Energy may use the engineer may use the FEM to minimize the number and conduct simulated tests to refine their design. This is an example of FAE analysis. Thank you.
Now we will go to the methodology part, which will be presented by me, Norifa Safira. So our group choose the reverse engineering for our process flow. Let's see the first step. Firstly, the turbine propeller is scanned in order to generate the points cloud. Next, we will validate the properties of turbine propeller by using two softwares, which is CES EduPack 2019 for selecting the best materials and ANSYS software for finite element analysis, or we call it as a FAE. Last but not least, we will do the inspection of turbine propeller to see the variety of geometry and dimension. Next is description. This description is more likely as an expected characteristic when producing the turbine propeller. So our first and main objective is we want to choose the material. So there are two types of material, which is nickel and titanium. The expected mass will be around 1.2 until 6.0 kg. The tolerance should be plus minus 0.1 mm. And lastly is the surface roughness should be less than 2 μm. Now the mechanism of turbine propeller. Generally, its function to flow internally, which similarly to one of the Kaplan, but with the fixed blades. It is also for operating at higher flow rates. Last but not least, the turbine propeller can produce propulsive thrust in ship and aircraft. So, as you can see at the left part, here is our drawing of turbine propeller. It is important to list out the bill of material, or we call it as BOM, and know the cost for the turbine propeller. We just used one part for our project and we decided to make it by using additive manufacturing. So, according from the resource, a trusted resource, which is from Zauba 2013, the actual cost to produce the turbine propeller for industry purpose is RM 228,779 ringgit and 11 cent. For the last part in methodology is to select the materials AM system. So there are two materials are chosen, which is nickel and titanium. Both materials are compared based on density, Young's modulus, fracture toughness, flexural strength, thermal shock resistant, and corrosion resistant. These materials is compared based on the information data that has been collected from CES EduPack 2019. Lastly, we to select the AM process. We found two suitable AM processes for our turbine propeller, which are LMD and DED. Both process can be applied in metal and alloy. However, only LMD can be applied for composite. The LMD tend to produce a better surface finish with the high accuracy. Unlike the LMD, the DED will give a higher cost in producing our turbine propeller.
Let's continue to chapter 4, the result and discussion of this study. In this chapter, I will discuss the comparison of the new and old product of the turbine propeller. Here, I will justify the difference that have changed from old to new design production. The method that have been used in the study for drawing and analysis is CATIA and ANSYS software. Comparing the old and new design. This study compared the design of turbine propeller, where left is old design while right is new design. Diagram left shows the propeller for old design. This design used 10 number of blades, while the right diagram is the new design propeller with 25 number of blades. This new design is to improve the performance of the turbine propeller, where more blade is used. Next, we go to the percentage of part reduction. In this part, the mass is compared to show the difference of the mass from the old and the new design. It shows that there is difference on the mass of both design. The old design recorded higher mass than the new design. By using the percentage of reduction, it is reduced until 38% of mass when calculated. This is because of the material changes from nickel alloy into titanium aluminide alloy. And we continue to the feasibility and improvement. In this section, the explanation of feasibility and improvement made from the old design of turbine propeller into the new design. The major improvement of the turbine propeller is the addition of the number of blades used. As studied, the old design of the turbine propeller used 10 number of blades, while the new design of the propeller used 25 numbers of propellers. This is proposed for a new design because of the better performance, where increasing the number of blades could provide more compression of the turbine propeller when assigned. In addition, the material of the propeller also have been changed, as the old design of propeller used nickel alloy for the material of the propeller. Nickel alloy commonly is used for the Euro engine and gas turbine, which effectively in 4000 degrees Celsius temperature. So, for the new design of the propeller, will be changed into titanium aluminide alloy. The titanium aluminide alloy has particular weight of about half of the nickel alloy and is adequate to provide a spatial force in region of hot temperature. So we suggested to use the titanium aluminide alloy as the material most likely used because of the lightweight. Lastly, this study aims to reduce the weight of the turbine propeller and improve the performance of the propeller. Even the weight of the propeller can be reduced, the strength of the propeller might be better on the old design rather than new design. This can be justified from this study. Next, we go to the mechanical properties and analysis. These are the properties that have been analyzed for this study. First, the mass of the old and new design. Secondly, the material used for propeller. Third, the equivalent stress of both design. Lastly, the safety factor that shows two different safety factor value. Here shows that old design are much more better because generate nearest number of safety factors into the ideal safety factor, which is 1. Okay, we go to the summary of this chapter. This chapter explains the result and discussion of the design, drawing and analysis by using the CATIA and ANSYS software. This study showed that the old design of turbine propeller is improved by increasing the number of blades and reduce the weight at the same time. All the analysis is stated in this chapter, which could help the industries of aerospace or aircraft for manufacture. Even though this study achieved to reduce the weight of the old turbine propeller, the equivalent stress for the old design is higher than the new design. This is because the old turbine propeller is using the nickel alloy compared to the new design, which is titanium aluminide alloy. If the new design goes to economical product requirement, it might will be the best design proposed because of lightweight properties for the turbine propeller.
The conclusion for this project is students will demonstrate the capabilities of AM through this evaluation of the project. In improving a product's consistency, the AM approach is strongly encouraged. The ability to minimize the mass of turbine propeller from existing turbine propeller by using topology optimization is predictable based on project analysis and outcome taken from the discussion. Since the goal is accomplished, the product design achieved the aim. Students are able to present a comparison of the manufacturing technique with AM for turbine propellers with a topology optimization approach based on the result. Optimizing topology is a very useful area to explore, as most businesses really need continuous improvement to maximize efficiency. Finally, the advantage of AM learning in this project is that students are able to prepare creatively without thinking about the cost and time.